Yes, friends. Uh, so in this class, we are going to start a new model, that is model number 2 of your syllabus. So that model 2 is about the modelings. So in that, it is a mathematical models. Model 2 mathematical models. So objective of this model is to develop a mathematical model for the mechanical, electrical, servo mechanism and the hydraulic systems. The objective of this second model is to develop the mathematical model for the mechanical, electrical, servo mechanism and hydraulic system. We are going to develop some models. So which type of models? Those are the mathematical models. Mathematical models for the mechanical, electrical, servo mechanism and hydraulic system. So these systems are used in the control system. So all these systems are used in the control system. So we can develop the mathematical model for all these type of system. Okay, so let us start with, before going to develop mathematical for mechanical, electrical, servo mechanism and hydraulic system. Let us start what is the modeling of control system. First we should know what is the modeling of control system. The first step in the design and the analysis of control system is to build physical and mathematical models. To build physical and mathematical models. So if you consider any control system, so before going to install that before going to use that control system, we need to design that control system, and also we need to analysis of that system. We need to analysis of that control system. So to design and to analysis of those control system, first we should develop the physical and mathematical models. First we should build the physical and mathematical models. Okay. Next, a control system being a collection of several physical systems. So as you know, if you consider any control system, it is a collection of several elements or several physical systems. So in that physical system, there are some subsystems also there. Okay, it may be of mechanical systems, which may be of electrical or electronic systems, which may be a thermal systems. Okay, which may be hydraulic or pneumatic type of systems. So first, a control system is a collection of several physical system which may be those physical system may be of mechanical, electrical and electronics, okay, thermal, hydraulic or pneumatic type. Okay, so first, why we need that modeling of control system? In order to design and analysis purpose. In order to design and analysis purpose, we need a physical and mathematical models. We need a physical and mathematical models. Okay, to analyze and the design of any control system, we need physical and mathematical models. Okay, a control system being a collection of several physical systems. So those systems may be of mechanical, it may be of mechanical system, it may be of electrical system, or it may be of electronic system, or it may be of a thermal system, okay, or it may be a hydraulic or pneumatic type of system. It may be consist any type of systems. So that is control system. Okay. Next, idealizing the assumptions are always made for the purpose of analysis. So while designing or while analyzing, we have to make some assumptions. We have to make some assumptions. So those assumptions should be idealizing. Okay. So those are purpose of analysis and synthesis. So those assumptions are purpose of analysis and okay, analysis and synthesis. An idealizing representation of physical system is called as a physical model. So that idealized representation of any physical system is called as a physical model. It is a physical model. So here in the first step in the design and analysis for control system is to build the physical and mathematical. What is the physical models? an idealized representation of physical system. So in the suppose you are going to make one control system, first we should represent that system with a physical system, means how it will look, what is the physical observation of that system. So it is called as a physical model. So next, process of obtaining the desired mathematical description of the system is called mathematical modeling. So that first physical system is nothing but how its physics involved, how its physics involved. So what is the shape, what is the size, okay, what is the length. So all the dimensions, what is the requirement of that system. So that is coming under the physical system, how it looks while using that actually. Okay, so what is a mathematical modeling? Description, process of obtaining the desired mathematical descriptions. So that system is described in the mathematical format. So that system or physical system, so that is described in the mathematical description. So that system is called as a mathematical modeling. It is called as mathematical modeling. Okay, so that system is called as a mathematical modeling. Next, I think you understood this. What is a mathematical models? Modeling of control system. So why need that modeling of control system? To analyze and the design. Initial step of the your manufacturing. You can say it is a if you want to manufacture any control system or install any control system, first we need to design that and analysis. So for that we need that modeling. So there are two types of modeling. One is physical models and the mathematical models. What is the physical models? It is a collection of several physical systems. Several physical systems. So those physical systems may be of mechanical type of physical system, or electrical type of physical system, or thermal type of physical system. Okay, or hydraulic and pneumatic type of physical system. So next, idealized assumptions are always made for the purpose of analysis and the synthesis. So these assumptions are made while designing or analysis. Some assumptions are taken. So those assumptions are made for the purpose of analysis and the synthesis. For the purpose of analysis and the synthesis. Okay, an idealized representation of a physical system is called a physical model. Idealized representation. So you have to represent that physical system in idealized way. So such a systems are called as a physical model. So what is the mathematical model? The process of obtaining the desired mathematical description. The process of obtaining the desired mathematical description of the system is called mathematical modeling. So we have to describe that physical system in terms of what? Mathematical form. What is the mathematical formation? How to describe that in mathematical formations? By using the formulas, or by making some formulas regarding that physical system. So that is called as a mathematical modeling. What is the physical modeling? Physical modeling is a physics, how it looks, what is the dimension, what is the shape, how it looks, that is a physical. Okay, so mathematical modeling means so that physical system is going to be described in the mathematical form. Mathematical means by using some formulas, okay, by using some techniques, by using some methods. So you have to describe that physical system. So that is called as a mathematical modeling. Okay, next, modeling of mechanical systems. So here the modeling has been done. Mathematical model for the which type of systems? Mechanical, electrical, servo mechanism and hydraulic system. Okay, so first we have to study with mechanical modeling system. So that is modeling of mechanical system. Later we discuss about the modeling of electrical system, modeling of servo mechanism and modeling of hydraulic system. So today we are going to start the modeling of mechanical system. So next, modeling of mechanical system. So mechanical system can be idealized as a spring mass damper system. So in the mechanical system we have to idealize it as a spring. mass and damper. So these three main components. So these three are in the mechanical modeling system. Mechanical modeling system. Okay, and governing the differential equations can be obtained on the basis of Newton's second law of motion. Newton's second law of motion, which states that F is equal to ma. F is equal to ma. So in the mechanical system, you can idealize that mechanical system as a spring, mass and damper system. So these three systems are considered as a mechanical systems. We have to governing the differential equations. So we have to governing the differential equations for these three systems by on the basis of what? Newton's second law of motion. We have to apply the Newton's second law of motion to the spring, mass, damper. So all these are considered under mechanical system. Mechanical system. In the mechanical system, you have to consider that system as a spring, mass, damper. So we have to develop, or we have to governing the differential equations for spring, mass and damper on the basis of Newton's second law of motion. Newton's law, second law of motion, which state that what is the Newton's second law of motion? F is equal to ma. F is equal to ma for a rectilinear motion. So here F is the force, m is the mass, and a is the accelerations. Accelerations with consistent units, with their units as usual units. So next. T is equal to I into alpha. T is equal to I into alpha or J into alpha or J alpha for rotary motions. For rotary motion, this is a rectilinear motion or reciprocating motion. This F is equal to ma is for reciprocating motion or rectilinear motion. Here T is equal to I alpha. T is equal to I alpha or J alpha for a rotary motion. So in the mechanical system, when you call that system is a mechanical system, it should either have reciprocating motion or it should either have rotary motions, reciprocating or rotary motion. Then only the system is called as a mechanical system. So when we call one system is a mechanical system, that system is having either rectilinear or reciprocating motions or rotary motions. So for reciprocating or rectilinear motions, F is equal to ma. This is a Newton's second law of motion. F is equal to ma. Okay. For rotary motions, we have to take the torque T is equal to I alpha or J alpha for rotary motions. Okay. Next, where T is equal to torque. Where T is equal to torque, I or J is the moment of inertia. I or J is moment of inertia. Alpha is the angular accelerations. You can sometimes you may take that omega W. Instead of alpha, we can take that omega. That is angular accelerations with their consistent units. So first, so listen here. The modeling of mechanical system is idealized as a spring, mass, and damper. So my mechanical system is idealized as spring, mass, damper. So the governing equations for spring, mass, and damper can be obtained on the basis of Newton's second law of motions. On the basis of Newton's second law of motions. Which state? What is the Newton's second law of motions? F is equal to ma. That force is equal to mass into acceleration. So this Newton's second law of motions is applicable for the rectilinear or reciprocating motions. This F is equal to ma is applicable for rectilinear or reciprocating motions. Okay. So here F is equal to ma. This is one formula. But our mathematical model. This is nothing but our mathematical model. It is a mathematical modeling. So and T is equal to I alpha. You can say in some times you can use this alpha as a omega. Alpha as a omega. Okay. So both are same. So here we can use this where T is equal to torque. I or J is the moment of inertia and alpha is angular accelerations. Angular accelerations. Okay, we have to apply the Newton's second law of motion to the spring, mass and damper. Spring, mass and damper by to get the mathematical models. To get the mathematical models. To get the mathematical models. Okay, so next one is continuation of that mathematical models. Okay, sorry, mechanical modeling system. So in that mechanical system can be of two types. Mechanical system can be of two types. One is a translation system and another one is rotational system. First one is the translation system. Second one is rotational system. The mechanical system. As I already told you that the system which is said to be a mechanical system, it should have either rotary motions or it should have either translation motions. Okay, that's why it is called as a mechanical system. So here in the mechanical modeling system, the mechanical system can be of two types. One is a translation system, second one is rotational system. Okay, so in the variables that describe the variables that describe the motions are displacement. Okay, so in the mechanical systems, the variables which describes the motions, displacement, velocity and acceleration. So these three variables are describe the motions. So in order to describe the motions, so we should know the displacement, velocity and the acceleration. And also we have three parameters. We have three parameters. What are those? Mass, which is represented by m, mass which is represented by m, coefficient of viscous friction which is represented by the b, spring constant which is represented by k, spring constant which is represented by k. Okay, so mechanical system can be of two types, translation system and rotational system. Okay, the variables that describe the motions are displacement, velocity and accelerations. Okay, along with this we also have three parameters, that mass, coefficient of friction factor, okay, that is represented by b, spring constant which is represented by k. So in any mechanical system we need to describe that motion, so we have to take displacement, velocity and acceleration. We have to take the displacement, velocity and acceleration. Okay, so next one is in a rotational mechanical type of system, these are considered for the translation system. These are considered for translation systems. For rotational mechanical type of system, we have three variables. We have three variables: torque which is represented by the t, torque which is represented by t, angular velocity which is represented by omega, angular velocity which is represented by omega r. So in the previous equations we used that alpha. Okay, angular velocity which is represented by omega, angular displacement represented by theta, angular displacement represented by theta. So these three variables, these three variables are used in the rotational mechanical type, rotational mechanical type. So in the rotationals we are observing the torque. So due to torque only the rotations takes place. In the rotational type we are observing the torque, angular velocity which is represented by omega, angular displacement represented by theta, represented by theta. Okay, so this mechanical system can be of two types, translation system, rotational system. Okay, so that the variables that describe the motions are displaced are displacement, velocity and acceleration. Okay, so these three variables are, these three parameters for the translation systems and these three parameters are for rotational systems. Just remember these are the very important. Mass, coefficient of viscous and spring constant are used in the translation system. Okay, torque, angular velocity, angular displacement are used in the rotational mechanical types of system. Okay, so next one is, now we have to discuss it more. Now let us consider the linear displacement. So to describe the motion, to describe the motion of mechanical system, we have to consider the displacement. Here it shows the displacement. Okay, displacement mechanical system. which is shown in below. So here the figure shows the spring mass mechanical system. Spring mass mechanical system. So this is a spring and this is a mass. This is a mass. Okay. So now let us consider the linear displacement. So which type of mechanical type system it is? Translational. Why it is? It is having the linear displacement. Linear, not the rotary displacement. It is having linear displacements. That's why it is a translation. Translation type of mechanical system. So usually in the mechanical system we have to consider three components, that is a spring, mass and damper. Spring, mass and damper. So in this let us consider only two components, that is spring and mass. That's why it is called a spring mass mechanical system. Spring mass mechanical system. Okay. So next we have already marked various variables in the diagram itself. So these are the variables, that x, k and f are the variables. So we have x is the displacement as shown in the diagram. This is the x is the displacement. This is a displacement as shown in the diagram. So now we have to apply the from the Newton's second law of motion. So we can write the force. We can write the force, that F1 is equal to m into acceleration. The acceleration is nothing but meter square per second square, meter square per second square. So that is indicated by dx square. This is the displacement, dx square by d square y, dx square by d square y. That is f is equal to ma. This a is nothing but acceleration, that is dx square by d square y, plus b dt by dy, b dt by dy. So this is the damper. So that mass, sorry, spring. This is a spring. Okay. B dt by dy plus damper, that is k into x. This is a spring where k is the spring constant and this x is representing the displacement of the spring. Okay. B dt by dy is equal to what? This is a damping. So it involves all three equations here. This is a mathematical modeling. We have to describe this physical system. Physical system in mathematical descriptions. Physical system in mathematical descriptions. Okay. Next. So in this F1, F2 is nothing but P dt by dx. Okay. And F3 is kx. F3 is sorry, it should be a y. It should be a y. Okay. So next F2 b dt by dx, f3 is equal to kx. Next, from the diagram we can write the f is equal to f1 f2 f1 plus f2 plus f3. So f is equal to what? F1 f2 f3, f1 f2 f3. Okay. So this is a damping, this is a spring and this is a mass. So this b is representing the damping. Okay. So that f is equal to what? F1 f2 f3. So this f1 is something but this f2 and f3. This is f2 and this is f3 and this is f1. So f1 is considering all these parameters. Okay. So next, from the diagram you can see that f is equal to f1 plus f2 plus f3, f1 plus f2 plus f3. So on substituting the value of f1, f2 and f3 in the above equations and taking the Laplace transfer, we have the transfer function as p is equal to 1 by ms square plus bs plus k. So this Laplace transfer, how to take this Laplace transfer? S square is nothing but what? Dx square by dy square is nothing but yes. Or you can say that dt by du, differential with single order is taken as a s, but it is differentiating twice, that's why it is a s square. Okay. And this b dt by dy is nothing but bs, this is a s, Laplace transfer of dt by dy, and the k. So here it is Laplace transfer of x is 1. Laplace transfer of x is 1. That's why it is a k, only k. So output is transfer function is already we know that transfer function is given by output by input. So these are the input and this is the output. Output by input. This is our transfer function for the Modeling of mechanical system. Mechanical system transfer function is 1 divided by ms square plus ps plus k. This is very important to remember. Okay, p is equal to 1 by ms square plus ps plus k. Okay, so these are the modeling of mechanical system. Okay, next. So in the next class we are going to discuss the mathematical modeling of electrical system. Mathematical modeling of electrical system. So this is also similar to the modeling of mechanical system. Next we are going to study the mathematical modeling of electrical system. Okay. So we will discuss it in next classes. Okay. Uh, Thank you.